Okay, so it's our, I guess it's our second control seminar for the semester. Once again, we've got a football game tomorrow. So what that means is it's impossible to invite a out-of-town person. The upside is we get one of our distinguished local people to speak. And so today we have Professor Jeffrey Scruggs to present for us today. He's in the Department of Civil Engineering, Civil and Environmental Engineering, I guess if I say it correctly.
I don't know anything about environmental engineering.
Got a number of awards. NSF Career Award was one of them. And then I looked up this morning, you'll have to tell me what this is later, the Berker and Gojidit Fellowship or Faculty Award. He's been doing some nice work in energy harvesting, and I think he's going to tell us about some of that today.
Sure. Thanks, Pete. Thank you, everybody, for coming. What I want to talk about today is actually mostly the work of my PhD student, Connor Lagakis, sitting right over there. So if you're interested in anything that I say today, Connor can probably answer your questions at least as well as I can, if not better. He was just helping me generate some plots for this presentation earlier today because I couldn't figure out where my code was going wrong. So Connor is the expert. But what I wanted to tell you about today is a project that I've been playing around with since my PhD, which was, well, I defended my PhD in 2004, and I was playing around with this problem then. It's one of my favorite problems, and it's one of the hardest things I've worked on. And it has to do with what I'm calling self-powered control. And for those of you wondering, this is not the same as perpetual motion. It's not the same, so don't worry. This is, yeah, you know, as Pete said, I'm a professor of civil engineering. So something that I like to work on is these types of vibration suppression problems. And you can't really see the lines too well there, but you know, buildings that have actuators in them that you use to control the deformation of the building during earthquake and high winds to prevent structural damage and to ameliorate high accelerations. And these types of control systems have been shown to be extremely effective at protecting infrastructure and making it more resilient. Yeah, so the use of actuators to reduce dynamic response of a passive plant doesn't have to be a building. It can be any passive plant subjected to exogenous disturbances like earthquakes and winds. The control objective is to simultaneously reduce structural strains as well as absolute accelerations. And one of the things that, you know, if you go to a civil engineer and you tell them you want to do this, they kind of look at you askance and say, well, that sounds crazy. And then they ask you where the power is going to come from. So active control is control that is presumed to be powered by a source that is unrestricted. So for example, you have your entire control system for these 4 buildings connected to the local power grid. And you know, it's interfaced through a transformer. Then you have the local AC bus here, and then you have AC to DC conversion to your DC buses that are what interface through power electronics with your actuators. Now the problem is, if we assume this control system has unlimited power, then extremely high performance can be achieved. But in this case, the control system is only as reliable as the power grid on which it depends. It doesn't matter how fancy the robust control theory is that you throw at the problem and how many theorems you prove. Ultimately, the reliability and robustness of the system is compromised by the fact that you're relying on external power, which is oftentimes non-reliable during extreme events, which are exactly what you're trying to protect against, right? Okay, so this is a major adoption barrier for this technology in civil engineering. I mean, there are other adoption barriers. It's expensive and it's complicated and so forth, but this is a big one. And so a lot of civil engineers in the 90s started thinking about, well, how can we do control without power from anywhere? One idea is this notion of self-powered control. So you have these same buildings, same actuators, but instead of connecting to an external grid, you just connect to a local bus, and that bus is interfaced with energy storage down here. And sometimes you control your actuators like generators to deliver power to the bus, and that power is then sent to storage where it's where a fraction of it is stored. And then at other times, you take that energy back out of storage and drive it back into the plant as necessary in order to achieve your dynamic response objectives. And in general, you may have some of your actuators driving power into the plant, other ones extracting power from the plant. The energy storage device is acting as the buffer that smooths out the power flow to the DC bus there. And of course, the one caveat is, well, you might run out of energy, right? So the control design problem that I'm interested in is we want to maximize performance subject to constraint that the storage system never runs out of energy. So this is an interesting type of constraint to impose on a feedback problem, and it's for those of you who are far enough in your PhD studies, you may already be kind of thinking, well, this kind of sounds like he's talking about passivity. Well, yeah, I am talking about passivity. It's very much related, but we'll get into that. So the advantages of self-powered control relative to active control technologies are pretty straightforward. We have what's called energy autonomy, right? It's a completely isolated, self-contained system that's imposing control without having to be powered by anything ever. And it just extracts all of its power from the exogenous disturbances, which makes it reliable and, of course, efficient because it doesn't require any power delivery. It's also has some really nice stability and robustness properties if the plant is passive. I'll talk about those in a minute. And its advantages relative to passive devices, like just basic, classic civil engineering devices to suppress vibrations, tune mass dampers, and shock absorbers, and passive devices like that. Well, the advantage is that we can realize more sophisticated or adaptive control laws that can change their dynamic behavior to accommodate different circumstances. And also, they can have more compact hardware realizations for the type for a given feedback law. For example, you can extract power at the roof and drive it directly and instantaneously into the base, and vice versa. You can circulate power through a system in a way that is very difficult to achieve with mechanical devices. So if you go back in the literature and look for where this idea started, it depends on how far you want to stretch the idea, but I like to draw a line in the sand in the mid-90s. This idea, as far as I know, was first proposed in the mid-90s by Donald Margolis, who's a professor at UC Davis, and his then, at the time, student Mark Joly, who's now with Lord Corporation. So they were looking at automotive suspensions. And these two figures are from their first paper on this. So they have some type of energy transformer that they're interfacing with an energy storage element through PWM force control. And of course, they have energy management devices there shown generally. Now, the motivation was to provide better cabin isolation than could be achieved with passive vibration absorbers while maintaining energy autonomy. They wanted their system to not have to be powered by the car itself. They wanted it to power itself, but they wanted to do better than they could do with these shock absorbers. So they proposed a concept more generally, but the focus was on hydraulic power transmission and accumulator energy storage. So they built this self-powered actuator entirely out of hydraulics. They designed feedback controllers with what they called regenerative constraints, which impose the constraint that on average, the power injection into the plant has to be negative. So on average, it has to extract more energy than it's driving into the plant. So several other proposals for regenerative suspensions emerged around the same time in the late 90s. And there was another important paper in the Journal of Sound and Vibration by Nakano, Suda, and Nakadai in 2003 that proposed an electrodynamic or electromagnetic transducer for self-powered systems. And that's one of the first papers that effectively demonstrated that experimentally. A lot of people have followed up on that with energy autonomous electromagnetic actuators for vehicle suspensions. These are just 3 of many papers. Some of you might know the second author here, Lezo. We just hired him at University of Michigan in the name department. Lei, if you're listening, he made the list. There have been a number of prototypes that have been successfully demonstrated at the automotive suspension scale. These are just 3 examples that I picked from papers. This one here is actually the one that my lab works with, and I didn't have a good photo of it on hand. The diagram was better. So these are just 3 examples of devices about this big that do the job of self-powered control. So in principle, many of these devices scale up to civil scales. Hasn't really been done yet. I mean, nobody's actually ever implemented a self-powered control system at a civil scale, but physically, there's no reason why they couldn't. It's a matter of cost and logistics and so forth. Now, more recently, just in the last 6 or 7 years, in the area of robotics, they've become very interested. A lot of people in the robotics area have become interested in energy-aware control, as they're calling it. And so especially in the area of robotic prostheses, for example, for lower limb prostheses, the use of regeneration to recapture the energy driven into the prosthesis by the host during the in-swing of the limb to recover the energy that's injected during the outswing, vice versa. So there are just a few examples here, and I kind of started collecting some examples and putting them on the slide and realized that I was going to run out of room on the slide eventually. This has become a hot area. You might notice Bobby Gregg's on there. There are a few other names on this list that you might mention. I do want to give a shout out to Hans Richter there, who's one of the first people that I know of in the literature who has looked at these self-powered robotics applications specifically and demonstrated them experimentally. He has in his lab, he's developed these self-powered prosthetic prostheses for lower limb prostheses. Diagram here that shows you that it's interfacing a motor with a supercapacitor for energy storage and successfully capturing energy from the host to power itself. So there are actually a lot of other applications as well. It depends, like I said, kind of depends on how far you want to stretch the idea of what self-powered control is. There are connections, for example, to the energy storage devices that smooth power after it's generated by a renewable energy source like a wind turbine. There's also a connection with, as you probably might have guessed, with power management systems in electric vehicles and hybrid electric vehicles. In particular, vehicles that have hybrid energy storage systems that split the energy storage between a supercapacitor and a battery. They have to manage that flow of energy. It turns out you can model those also as self-powered control problems. So now, 15 minutes into the talk, and I'm finally at the outline. First thing I want to talk about is just a bit about the system modeling, because it turns out that modeling is kind of important. We can't just dive straight into the control theory, but we'll get to that. I'll talk about the self-powered feedback design problem in a kind of formalized setting. And then the main thing that I want to tell you about today is 2 theorems. The first one is a necessary condition for self-powered feasibility, and the second is a sufficient condition. And these are important because they allow us to see how the parameters that characterize the hardware that's used to realize one of these systems impinge upon the feasibility domain of the feedback law. I'll talk a little bit about some extensions at the end of this. Okay, so I'm going to assume that we're building a self-powered control system in an electromechanical mechanical way. So you have your plant here, it's excited by the exogenous disturbance W, and it has embedded within it N sub P transducer ports. So we can think of these as being, for example, permanent magnet electric machines, but they could also be other types of transducers that convert energy. The point is that we just have N sub P ports. And each one is associated with a voltage and a current. So we say that the voltage is co-located with the current, so V and U. So the power electronic blocks here, these blocks that say power electronics, are what regulate the currents to be desired values. So we have desired currents U1 through U star 1 through U star NP, and we have real currents U1 through U, and we have power electronics that facilitate tracking between the two. We assume that each of these power electronic blocks has in it a pretty basic PI tracking loop that does a high bandwidth force track or current tracking between the U stars and U's, and we assume that the losses in the power electronics have been absorbed into these resistances here, these R1 through RNP shown there. So those resistances are outside the power electronic blocks, but for the purpose of coming up with a tractable model, we're going to assume that we're somehow able to absorb the dissipation in the power electronics into those resistances. Now, the feedback controller K is, well, in general, takes some measurements Y and produces those current commands for us. And the energy storage subsystem down here is modeled as a supercapacitor. You note that, and this is really the reason why the talk is not 15 minutes long, we have these two resistances here, R sub R and R sub S, that characterize the parasitic losses in storage. Those characterize losses respectively when we transmit power to and from storage, that's the R sub R, and when we the energy alone, once it's there, it eventually decays away with that decay depending on the type of storage you're talking about. The DC link here is just a small capacitor that facilitates the flow of power between the different components. It's I'll say more about that in a minute. So I'm going to make three assumptions here in how we model this system in order to come up with an analytically tractable model of the evolution of energy. The first one that I've already mentioned is that resistors R1 through RNP, as well as these two resistors here, R sub R and R sub S, these capture all of the dissipation in the network. So I'm able to somehow lump all of the dissipations and the power electronics and everything else into those resistances. Now, technically, the power electronic blocks are comprised of MOSFETs, switches, and inductors, both of which dissipate power. We're assuming that we've been able to lump those dissipations in with the resistances to the left there. The power electronics are operated in switch mode pulse width modulation, which is highly efficient. You can oftentimes get efficiencies well above 90%, so it's not a terribly bad assumption to make. Second assumption is that the power electronic controllers facilitate high bandwidth current tracking between U and U star, where U and U star are both vectors. So the pulse width modulation, for those of you who, I mean, I think probably a lot of you know about PWM, but in case anybody doesn't, it basically just alternates switches back and forth at high frequency. And as a consequence, the currents are controlled in a manner that looks sort of like a triangle wave here that sort of oscillates about its value. And if the PWM switching frequency is sufficiently high, the ripple in that current is sufficiently small. The DC link is assumed, the capacitor CL is assumed to store negligible energy. Now, what that enables us to do is to assume, at least approximately, that the net power flow into the DC link at every time is 0. So we're assuming that the DC link does not store significant energy to make it so that we actually have to model the dynamics of that stored energy. We assume that the DC link is essentially a node that stores no power. Okay, so now if we make those assumptions, and here's what happens. We can come up with a differential equation that characterizes the stored energy in our energy storage subsystem, which is just 1/2 times the capacitance times the voltage squared. But if we write the differential equation for the energy directly, we get this thing. Now, this is why this area is interesting is that this is a nonlinear differential equation and has this square root in it that has an argument that may not even be, positive. And so what does that even mean? We have these two parameters, tau sub s and tau sub r. These are time constants that are related to the resistance r sub s, r sub r, shown here. Remember, these are these two resistances in the storage system there. And really, the values of those resistances are not nearly so important as these time constants, tau r and tau s. So we can define then trajectory feasibility. If I talk about a particular trajectory for the voltages in L2, then I can say that for a given set of parasitic loss parameters, R, tau S, and tau R, and for that trajectory of voltages, I can define this capital U here as the set of all current trajectories such that the stored energy is a real positive number for all real positive time and for all initial conditions that are real and positive. So in other words, I'm saying that this capital U here contains all the trajectories for current that are such that when I integrate out this differential equation, I get a physical value of an energy that's a real positive number. So if a current trajectory is not feasible, it's not physically realizable by the system. So parasitics are parameterized by this triple R, tau R, and tau S. And we've already talked about what R is doing. It captures the transmission losses in the power electronics as well as the transducers. Tau S characterizes is the characteristic decay time of stored energy leakage. So that has to do with essentially the amount of time that the storage system can hold on to energy once it's delivered to it. And tau R is a little bit harder to understand what that is. So here's the deal with tau R. If we think about two power quantities. PE is the power that flows from the DC link here to the plant and everything else. So it's the power flowing from the DC link to the plant. And PS is the power evacuated from storage. Now, if we were talking about a perfectly efficient system, the two would be the same, right? But it's not perfectly efficient, and in particular, you have this resistance in the way there. So if you make a plot of the relationship between PE, power into the plant, and PS, the power that's evacuated from storage, you get a parabolic curve that looks like this. And it's a sideways parabola in the sense that it goes up to a vertical tangent there. So what happens here is that if you demand a certain amount of power out of the DC link to the plant in order to do control, you can see that there's a limit beyond which storage system simply cannot deliver power to you. It chokes. And so that maximum PE, that PE max, is related to the stored energy. So the more stored energy you have, the more power you can deliver for this storage model. So tau R is the ratio of those two. And so we can actually think of tau R as we can view it as the ratio of energy density over power density for storage systems. And if you think about different storage technologies, that ratio is going to look very different. So these things are called Ragon plots, and power density on a log scale here, energy density on a log scale, and different types of storage technologies. Diagonal lines characterize tau R values. So tau R is kind of important because it's what makes the problem really interesting. It makes the differential equation for the energy storage nonlinear, and it also means that there are trajectories that are simply not feasible because the storage system cannot deliver power that's being demanded. So we can then, now that we've formalized the notion of trajectory feasibility, we can now talk about a self-powered feedback control problem from a mathematical perspective. Self-powered feedback design pertains to this diagram shown here, the block diagram on the right. The design objective is to optimize the feedback law K such that the closed loop transfer function or closed loop mapping from W to Z is favorable in some sense. For our purposes, it doesn't really matter what that means by favorable. We can choose some metric and say we're doing H2 design or H infinity or whatever. The design constraint on K is that the trajectory of currents has to be feasible for all V's in L2 plus. So we can then define self-powered feasibility in terms of the feasibility domain for feedback laws. K is called self-powered feasible if the current trajectory that it produces is feasible for all V in L2. And what that means, just to remind you, is that this differential equation here for the evolution of stored energy has a real positive solution for all real positive time and for all real positive initial conditions. And we're going to call this set of these self-powered feedback laws it's capital K. So it turns out that if we restrict our attention to linear feedback laws only, then K has to be co-located. In other words, there is no such thing as a self-powered feasible linear control law that is not co-located. And by co-located, we mean that V and Y are the same. So all we're feeding back is the voltages. We're feeding back the voltages and producing currents from them. So effectively, we're creating a synthetic admittance with the system. So this second bullet is I think I'll skip that in the interest of time. Third bullet here is important though. If K is self-powered feasible for some parasitic parameters R, tau S, and tau R, and it's co-located, then it turns out that it has to be the case that the negative of K is output strictly passive, which means that it satisfies this inequality for all V in L2 and for some small epsilon parameter there. Now, the reason, and that is fairly straightforward to show, and I'll actually revisit this in a few slides and explain where that comes from. But the reason that's important is that the fact that negative K is output strictly passive, but it's important because of the passivity theorem. So the passivity theorem has many variants, of course, but one of them is that we suppose that negative K is output strictly passive, and the plant P satisfies two properties. One is that it's passive, and the second one is that it has bounded L2 gain. Then it turns out that the closed loop system has bounded L2 gain as well, guaranteed. So it doesn't matter how much model uncertainty you have, you're cooking robust stability into the technology that you're using for control because it's a bounded energy system. Essentially, you're making it so that if you design a controller that is not robust, that tries to destabilize the plant, something will saturate, something will switch off, the system will break down and not be able to realize that feedback law. The physics of the system is what imposes robust stability. It's not anything that we need to prove to ourselves in terms of our feedback laws. So now this is important because in many applications, the plant is guaranteed to satisfy both these requirements of the physical conservation laws. Buildings do, for example. Many systems are passive and many systems have bounded L2 gain. So in this case, unconditionally stability robust controllers follow. So now to the main order of the day, I wanted to tell you about these two theorems that we've come up. Because the issue now is, okay, well, we know there's this self-powered feedback control problem, but we don't yet know how to characterize the feasibility domain for linear feedback laws in a way that's tractable. So the first theorem is a necessity theorem. And it says this, it says that a controller K is co-located, so it maps V into U, and it has a minimal realization shown here. It's an LTI finite dimensional controller. And K is self-powered feasible for a particular set of parasitic parameters only if there exists a matrix S, which is symmetric, satisfying these two matrix inequalities. Now, when the parasitic losses are negligible, R goes to 0, tau R goes to 0, and tau S goes to infinity, that's a perfectly efficient technology that is able to route power from one place to another without burning off any energy and can hold on to the energy for an arbitrarily long time. In this limiting case, these LMIs distill precisely to passivity LMI for the KYP limit. This one here. It says that the mapping negative K is passive if and only if there exists an S equal to S transpose such that this linear matrix inequality is zero. So these two here basically become this one in that limiting case. The conditions become more restrictive as we start to increase those parasitic losses from their ideal 0 points to something finite. And note that when for any tau r greater than 0, it's interesting that in order for a controller to be self-power feasible, it actually has to have a feature return. So D has to be non-singular. That's a mathematical formality, really. I mean, in actuality, there are some subtleties there. And also, in order for a controller to be self-power feasible, it has to be asymptotically stable. That's probably not too surprising. Okay, really quick sketch of the proof. So essentially, here's what happens. If you recall, the evolution equation for the stored energy looks like this. And we can show that the stored energy at any given time is bounded from above by this expression in the middle of the slide here, which is a lot nicer than the one at the top, right? And so it actually is a straightforward application of the comparison lemma then to say that in fact we can come up with this function b of capital T, which is expressed here, and which bounds the stored energy from above. Now, why is that important? Because then that allows us to say, well, if I find conditions that are required for B to be positive, they have to be satisfied in order for ES to be positive because it's an upper bound. Okay. So that's the first thing to recognize is essentially a comparison lemma result. The second thing to recognize is that if I just go back to this previous slide, you look at the evolution equation for stored energy. In order for that to be a real number at every time, it has to be the case that this thing in the square root here doesn't become negative. If that happens, then I lose feasibility. So I can reduce this feasibility condition down to an instantaneous condition that at every time this quantity in the square root has to remain non-negative. And that can be re-expressed as this inequality shown here on stored energy that relates it to U and V. So evaluating at a particular time capital T and using the step 1 result, I drop in my capital V of T there. And what I end up with is an equivalent statement that says that that it's necessary that this quantity V of T minus this stuff over here, if I take the infimium over all the possible trajectories for V, that has to equal 0. It can't be negative, in other words. If I minimize this quantity, I have to get something that's non-negative. But remember that this V of capital T here is an integral quadratic expression in terms of our response. So if I want to infimize this quantity in the curly brackets, that's just a sign indefinite LQ problem. I can solve that using Hamilton-Jacobi theory. So it turns out that that LQ problem ends up giving me a solution that tells me that the minimum is bounded from below if and only if this Riccati equation here has a bounded solution for all time. And the thing that makes it unusual is that we have this non-zero final value for the Riccati equation that has to be satisfied as well. Now, non-zero final values are not unusual, right? They show up whenever you have a final value penalty. But what's interesting here is that it plays a different part in coming up with necessity conditions. We take the limit as the time horizon goes to infinity. We get 2 necessity conditions. One of them because this Riccati equation has to have a stable equilibrium in the first time. And the second one because the final value condition has to be in the region of attraction of that stable equilibrium. And those 2 things together end up giving me those 2 linear matrix inequalities in the theorem. So that's, loosely speaking, where the theorem comes from. So now let's think about the parasitic loss parameter bounds. If we're suppose that we're given we're given transducer resistances R, we're given tau S, and we're given a control design, and we want to find necessity condition, an upper bound for the value that tau r needs to be, which tells us something about the energy storage hardware that would be necessary to realize a particular controller. So the problem is equivalently solvable actually just by solving a Riccati equation and finding an eigenvalue solution down here. So I can actually solve for that necessity bound on tau r by first solving this Riccati equation for S, plugging it into this expression here, which is the maximum eigenvalue of this matrix shown here, and that gets me the upper bound on the value of tau r. And we can find bounds on this bound on tau r as we vary tau s and r, the other parasitic loss parameters in the system, and we can come up with Pareto fronts that tell us, you know, how that value of tau r depends on the other losses in the system. So just as an example, again, civil engineering professor, so building here. So application details, it's all pretty standard stuff for structural control. Our control objective here is going to be to minimize a multi-objective H2 performance measure here. Just, you know, a bunch of response outputs, we take their squares expectations and we minimize the maximum points. Designing the controller, remembering that the controller, in order to be feasible, it's necessary that these two linear matrix inequalities hold for its state space realization. Well, you know, if you want to do H2 optimal control without constraints, that's easy, right? But as soon as you impose constraints on it, it gets hard. And doing constrained H2 optimal control with these constraints in play is a highly non-convex problem. And there really hasn't been, at least to my satisfaction, a very convenient solution to these types of problems. Now, this is a self-powered control problem, but these similar problems show up in many applications where you have, for example, passivity constraints imposed on feedback laws and things like that. So there is a methodology that Connor and I have been using to solve these problems. It's simpler, and essentially it breaks down the control design into two stages that ultimately result in a suboptimal feedback law. The first stage, we relax the constraint from the constraint that the stored energy be positive to this constraint here, which is considerably more relaxed. However, we can impose this constraint on the feedback design, and it's a convex optimization. So that kind of gets us a little bit of the way toward our control design in a convex optimization framework. Then, with that optimal control design in hand, we then take we characterize its state space parameters A1, B1, C1, and D1, and we keep A1 and C1, and then for B and D, we redesign them by projecting them onto the feasibility domain of the necessary conditions. Now, we have a particular way of doing that. If you're interested, it's, Connor, which paper is that? I can't remember now. 21. It's in our ACC paper from just this past time. So if you're interested in that design methodology, certainly have a look. But what that enables us to do then is to plot this upper bound on tau r versus the inverse of tau s for different values of transducer resistance to get an idea for the trade-offs at play with different parasitics in our powertrain. So you have that if your transducers are more efficient because they have a lower resistance, then your tau r value can be higher and vice versa. Now, keep in mind that this is a necessary condition for tau r. I'll get to the sufficient condition in just a moment. So sufficient conditions are sort of the flip side, right? I mean, the necessary conditions are nice because they provide a bound, but they're not something you can design with because you're not really sure if the condition that you have is tight enough to actually guarantee feasibility. Feasibility is guaranteed by sufficient conditions, not necessary conditions. So this is our second theorem. So our second theorem tells us that if we have a controller K with a minimal realization again, then K is self-powered feasible if there exist matrices P, symmetric, and X satisfying these two linear matrix inequalities. So they're different matrix inequalities in this case. And we have to have a dummy variable here. This X kind of plays the middleman between these two LMIs. So the sufficient conditions have the same basic features as the necessity conditions in the sense that they involve the parasitic parameters in a certain way. And they become increasingly restrictive as the parasitics become more and more lossy. As the parasitic parameters go to 0 and tau s goes to infinity, they also distill to the KYP lemma for passivity, which is necessary and sufficient in that case. And we can show that actually the conditions become necessary and sufficient in more general circumstances where all we have to have is a tau r goes to 0 or tau r goes to infinity. So they are conservative. They're only sufficient, they're not necessary, but in certain special cases, they become tight. So a few comments on the proof. I'm really going to skip over this because we're running a little bit behind. But the key insight for this proof, the thing I really want to impress on you here is that the way that we proved this was to say that, firstly, I'm going to take this controller and I'm going to represent it equivalently by this linear fractional transformation. So here I have this matrix Z and this dynamic system G in the feedback loop. And I'm saying that there is an equivalence between this LFT and the original controller. Well, the reason I'm going to do that is that it turns out that you can show that the current trajectory U is feasible if two conditions hold. The static matrix Z has to satisfy this matrix inequality here, and G has to be such that its output R has a norm which lower bounds the stored energy. And the second thing is the thing that's hard to prove. But that was our starting point for this. And we said, okay, well, how can we prove that this lower bound works out? Well, the details are actually, I think I'll skip some of these details because they are in a CDC paper that we published last year. The only thing I want to say is that essentially it comes down to something similar to another comparison lemma result. It's not quite the comparison lemma, but it's something similar. So suppose we're given again the transducer resistance R, a leakage time constant tau s, and a control design K. And what we want to do is find the largest value of tau R that satisfies the sufficient conditions. In other words, how inefficient can we make our storage system and still realize the control law? That's really the big question. Tau R is associated with cost, it's associated with mass. You want it to be as big as you can make it without compromising performance. So it turns out we can frame this using our sufficient conditions as this optimization here, which is quite convex because it has a product between 1 over tau R and P here, but it's quasi-convex because we can solve it through bisection. So the optimal value of tau R that you get there is conservative because it's a sufficient condition. It's not necessary, but it does provide us a design value that we could actually use. So if you go back to our previous example and you plot what necessary and sufficient conditions are for tau R as a function of your other parasitic parameters, you come up with plots that look like this. So this is the sufficient condition, which of course is more conservative, and the necessary condition up here. We know that any tau R above the necessary line here is completely out of it. There's no chance. And we know that any tau R here guaranteed to be feasible. This gray area here, still kind of up in the air. We don't really have an answer for that. And we can, again, go and characterize the trade-offs between all three parasitic parameters, R, tau R, and tau S, and come up with these sort of interlaid Pareto fronts here. And this is kind of the main result, because this is essentially a way to, just to take a step back, a way to say, okay, I've designed a passive controller for my system. I need to find hardware parameters that will allow me to realize it as a self-powered controller. What are the least efficient hardware parameters I can get away with? So this is what allows you to do that. What it shows is that there isn't a single answer to that. There's a Pareto front. It depends on where on that front you want to be. So a few extensions. First, linear time varying systems. If we want our feedback law to be linear time varying for some reason, it's no problem. Everything that I've talked about here extends. The only thing that you have to do is add this time derivative in the sufficient condition, and everything else stays the same. In fact, when we derived these conditions originally, we derived it for LTV first and then specialized it to the time invariant case. So we've applied this to a self-powered control for a vibratory system with a time varying mass, a situation where you have like a vibratory system where the mass is escaping over time, and so the mass decreases. In fact, the sufficiency condition also extends to infinite dimensional linear time varying systems, and that's hopefully going to be an attack paper we have under review right now. So look out for that, but that's the infinite dimensional case. You can do the whole thing using Volterra kernels. You don't even need to have a state space. The necessity theorem extends to finite dimensional LTV systems, although the criterion is not particularly practical, and that necessity condition is a newer result that we have, and we still are not quite sure what the most compact form of the LTV case is. Okay, so that's one extension. The second one is infinite dimensional systems. It turns out that you can frame the sufficiency condition entirely in the frequency domain. If you think about it in terms of this linear fractional transformation that I showed you in the proof for the sufficiency condition, so we design Z and G explicitly instead of designing K, then it turns out that equivalent feasibility criteria can be given as, well, this Z matrix has to satisfy this matrix inequality, and then G has to have a transfer function that satisfies this, well, positive real type condition here, and this final value or initial value condition shown there, which apply even if G has no finite dimensional realization. We've applied this to a study of self-powered fractional order feedback laws. And finally, non-colocated feedback. This is kind of the big deal in terms of extensions. Suppose that Y contains information other than, in addition to B. So instead of just feeding back B, we're feeding back other signals as well. We'd like to have a way to do self-powered control in that case. However, it's a fact that in order for a controller K in that case to be self-powered feasible, the dependence of U on Y must be nonlinear. It can't be a linear controller. So one thing we can do here is to go back to our LFT again. We have this linear fractional transformation characterizing the mapping from B to U. And I said that Z can be time varying and it still works. Well, we can make Z a function of Y. And so the question is, how do we do that to get to get favorable performance? And for those of you coming to the CDC this year, this is an advertisement. We will be presenting that at the CDC. We have what I think is a really nice methodology for designing how that nonlinear feedback law works. Essentially, what you do is you first assume that Z is constant, and you optimize Z and G in a non-convex optimization for like H2 performance or whatever. And then we found a way to vary Z based on Y so that you guarantee to make the performance better. So you have the second design stage guarantees to improve upon the first design stage. It's kind of reminiscent of Lyapunov-based redesign, which is a classic control technique. All right. So as a summary, self-powered control has a few useful engineering applications, and mostly historically in vibration engineering, but also increasingly in other areas such as robotics. For LTI, self-powered control feedback laws have to be co-located and passive, but these conditions are not sufficient, and they don't capture the effect of parasitic losses. So the feasibility domain for the feedback laws is parameterized by this triple of parasitic losses. R, remember, is the transmission loss term, and there was resistances. tau S and tau R have to do with the storage system. We've derived two theorems. One is a necessary condition and the other is sufficient to guarantee self-empowered feasibility. And it is important that these conditions are not the same. I showed you a plot. The necessity condition is quite a bit more liberal than the sufficiency condition. The derivation of a single condition, which is both necessary and sufficient, is, at least to my knowledge, an open problem. And that problem was the one that I kind of got interested in my PhD dissertation and continue to be interested in now. This is just as far as I've gotten, so I mean, this is all I know. Anyway, as I said, not perpetual motion, but self-powered and controlled. I'm happy to take any questions that you have. I love talking about this stuff, so if anybody wants to chat about this afterwards, I'll stick around as long as there is interest. Thank you.
Some questions if people have them, either in the room or on.
So for the gap between the necessary and the sufficient condition, I'm wondering maybe for the LMI conditions, you might assuming some underlying quadratic Lyapunov style things. I'm not sure, but I'm just thinking, is it possible that sometimes system is feasible, but there's no such quadratic form, but maybe we need some more complicated functions?
Maybe. What we do know is that even though that energy equation for the evolution of stored energy, it's complicated, but it is homogeneous. So it should follow from that the storage function, that sort of Lyapunov type function that you would use in the feasibility conditions, should have sort of quadratic growth in a particular radial direction, but that doesn't mean it's a quadratic function necessarily. But that's all we know right now. But you're right, it could have something to do with that. I mean, the sufficient condition was kind of like we tried something and it worked, but there's no saying that what we tried is the least conservative thing.
Questions? Ask a quick question. Are there simple cases where you know necessary and sufficient conditions? Like if I took a scalar example, you just brute force work it out even numerically by hand, what's the optimal solution? Like that, and then understand, oh, in the scalar case, it's not a quadratic Lyapunov function that's optimal.
Yes.
Yes, you have simple cases.
Yeah. If there are examples of scalar cases where you can actually just work things out, you have to go beyond just making it scalar to make it simple enough for that to work. So the examples are kind of toy examples at that point, but yes, there are special cases like that. There are special cases where you can show that the sufficiency proof is also necessary, but those are very rare.
This requires obviously, controllers and DC converters and some sort of switches, I guess, which is a DC converter. Like in large packs or large battery packs, we actually have balancing circuits for every single cell. We're doing there's the balancing circuit. Most of them are passive. So have you? Sorry, I came late. So have you looked at that?
No. I actually have stayed away from battery modeling.
No need for battery modeling.
Well, no. I mean, I've always presumed that the storage system was a supercapacitor rather than a battery.
Sure.
So it's interfaced with the DC link through just a standard power electronic converter. So there's and that would be that would have to be controlled actively, of course. I'm not sure I answered your question, but
Right, I'm just saying that in our current batteries, or think about arrays of capacitors.
Yeah.
We use passive balancing.
yes.
We don't actually have like, actively controlled switches that turn on and off.
Oh, yeah, I see what you're saying. Yeah. So I think the way to accommodate that inside this would be to change the assumption that there is an active power electronic converter between storage and the DC link.
Sure. So I think what I'm saying is, have you applied your methodology to understand how to select the resistance, the resistances that we put in the.
That would be very interesting.
Yeah, that would be very interesting.
But no, we haven't done that, and I'd love to talk to you more about that. I understand your question now. Yeah, we have not looked at that.
It's another application you mentioned at the beginning was, vehicle suspension, sorry, and mentioned these magnetorheological dampers. So are they, which are out there now, they are passive, or they have this energy?
Well, so MR dampers are kind of in the same boat as some of the self-powered stuff, in the sense that you need some power just to run them, right? And it's sort of power to keep the lights on, so to speak. And that's different from the power that's being absorbed from the plant and having to be, transmitted through the system. MR dampers actually consume a lot of power because you have to drive an enormous amount of current through the solenoid in the coil. So if you actually look at how much power they consume, it's significant. So I don't, if I had to pick a technology to use, I mean, I'm partial to regenerative electromechanical devices as opposed to MR dampers, partly because of that, and partly because they can be used as generators. And so, that also makes them more efficient.
Thank you.
Other questions? Okay, let's thank the speaker again.
Thank you, guys.
Good.